Oh, that's better. Okay. Anyway, so back to me. Yeah, I wanted to use today's time. I found some videos about come back to me. I don't know if any of you saw them already.
Yeah, I watched them except for the third one I couldn't access.
Yeah. Oh, sorry. You mean the link is bad?
The link is broken. Yeah.
Okay, I'll fix that. Sorry.
So I went on YouTube and just searched for something of the same title and watched it, but I didn't like it.
Yeah,
so I don't know if it was the right one or not.
I have to say, a lot of these videos are really either super geeky and not, or too much detail that doesn't really get to the heart of the concept. So I went through a lot of them this morning to try to just save you guys time. So the links I found, I can even spend a few minutes today looking at them right now with you, but maybe I'll try to do it verbally. The links I found were a lot of these videos were the ones that seem to be most succinct, have animation, so not just equations, but animations that actually are pertinent to the concept, basically. And they're not too long, so like 10 minutes or so. So I thought in terms of basically, I was thinking about this because I realized the readings are more assuming that people know something about what thermodynamics concepts are, and then of course it's implicit, right? So I thought I might make that explicit today. And also the question for the week is actually more creative than that. The question for the week, just to remind everyone, is after taking thermodynamics seriously, and I'll say why we think we can take it seriously, is basically being a little bit more future proof in how we think about energy and energy systems. In the following sense, this is my editorial. Okay, I feel that, and we'll come back to it again maybe later. I feel that a lot of the talk about sustainability and energy transitions and going from fossil to renewable energy solutions basically assume that everybody's going to be using energy as they do now. Like we assume that consumption patterns and the consumption levels are the same. Just have to find a different way to meet those demands, which is just, I think, crazy. Really, it's not a sustainable way to think. And thermodynamics gives us some really fundamental reasons why that might be the case. That is the case. But the question is basically what I asked people in my own field in media arts back in Montreal around 2010. And we were supposed to, we were faculty and artists, and we were asked to think about the future of media arts, and they were all talking about things like I don't know what, AR or VR or something like that. And I was saying, well, look, what if we can't assume one day that we can plug our computer into the wall and just get electricity coming out of the wall? Just don't assume that we have 24/7 AC, So what do we do? What becomes of our field as media artists and computer science people, things like that? And the room was dead silent, just silent. There was people didn't have any response to that. I was kind of shocked, actually. Disappointed, And then about 5 years later, I started asking my own questions, my own students in my lab, topological media. So same question, and I got dozens and dozens of responses. It's really interesting. It's a generational thing. Maybe also just people kind of in the field just take certain things for granted. That's infrastructure, electricity, right? You just took it for granted. So that's the spirit in which I offer the question to you all. Okay, I'm sure we'll get more thoughtful responses than from my colleagues back then. Of course, now it's different. Now I'm sure we may get more answers. Anyway. But let's go back to thermodynamics. So, okay, Tanya saw a little bit of that, and I don't know if you others saw. Maybe if you don't mind, I can show a few moments of the video. Okay, let me share what I found a little bit. But I'll verbally describe kind of the intro to these things. Okay, first, so. Okay, so typical thing is, I can't show this. So this is coffee cup, right? Can you see it? And it was black coffee. I poured some cream into it, stir it up, it turns brown. And this happens all the time. You can mix some perfume into the room, spray into the room, and after a while, it diffuses through the whole room, so you can smell it anywhere in the room, right? So those are natural processes. They kind of give you a natural, it's the idea of spreading, right? And mixing is natural. Or another example would be, I have an ice cube or a cup of ice and a cup of hot water, put them side by side, and they both come to equilibrium. Okay, so that's kind of the starting point in terms of macro thermodynamics. Okay, but why is it, right? Same thing. Why is it? Why is it that it doesn't go the other way? And that's very deep. That's a deep question. Why is it that if you look at the micro level in terms of the at the level of particles, let's say, these laws of physics are reversible. If you have two things bounce and hit and glance off each other, two balls bouncing off each other, you can reverse the film, and the laws of physics are the same. It doesn't forbid one versus the other. Okay, so there's a profound difference here between reversibility at the level of local physics, kinematics, right? Just things bouncing against each other. But then what happens when we have trillions and trillions of atoms bouncing around? Why do we see this kind of asymmetry in time? That's where thermodynamics comes in, right? So let me show this video. I have a chat here. Oh yeah, great. So let's share this. And just a minute, okay? Just a minute or two. Well, actually 3 minutes or 4, okay. So let me go to oh, I need sound. Hang on, I need sound. Give it back. Here it is. Okay. So this is just the part where we start talking about entropy at the kind of the small level, looking at individual molecules bouncing around. The basic idea is you have a bunch of energy, finite amount of energy. How did it get distributed? So let's just start with this.
Is entropy a magical force that overturns your furniture and creates havoc in your office or home? No. Entropy is a measure of the number of ways energy can be distributed in a system of molecules. Molecules in a system at equilibrium have the same average energy. However, at a given instant in time, it is highly unlikely that all of the molecules have the same exact energy. Molecules in a system are constantly interacting and transferring energy amongst each other. As a result, one molecule may have a certain amount of energy at one instant, and at the next, it could have more or less. Depending on the energy the molecule has, it will be able to access different energy levels. The total energy of the system determines what energy levels will be accessible to the molecules. Higher energy levels will not be accessible because the energy required to reach them is not available. So when we say that entropy is a measure of the number of possible ways energy can be distributed in a system of molecules, we have to account for all of the possible combinations. And the way we do that is by considering the microstates available to the molecules in the system. Let's use an analogy to understand the term microstate. Let's say that you have 2 dice. What are all the possible sums for a pair of dice? Pause the video here and take a moment to jot them down.
Sorry, keep going.
We would call these sums possible macrostates of our system. The macrostate doesn't tell us what each individual die reads when we roll them, just the total, or macroscopic view, if you will. What are all of the possible dice combinations that will produce each of those sums? For example, we can produce the sum of 3 by rolling a 1 on the first die and a 2 on the second die. Or we can roll a 2 on the first die and a 1 on the second die. So there are 2 combinations that will produce the sum of 3. The dice combinations that produce the remaining sums are shown here. We would call each of these combinations microstates that correspond to each macrostate. The microstate gives us information about the individual conditions of each die. We see that the most likely macrostate, a sum of 7, has the greatest number of possible microstates. When referring to the microstate of a system of molecules, we are looking at a snapshot of all the energy levels that the molecules are occupying at a given instant. Let us do an example using the idea of microstates to evaluate the entropy change for a process with which you might already have some experience. Take a look at these two brass bars. One has been heated to approximately 60 degrees Celsius. The other bar is at room temperature, approximately 20 degrees Celsius. When we push them together, what will happen? From experience, you probably know that the two bars will equilibrate to some temperature between the hot temperature and the cold temperature. Here you see infrared images of the two brass bars. The hot bar is red and the cold bar is blue. We can see the heat diffusing from the hot bar to the cold bar. But can you explain this spontaneous change in terms of entropy? Let's work through this together. Let's try to imagine what each bar looks like at the atomic level. Atoms in a solid are fixed on a lattice. They don't have the freedom to move much, but a very small amount of vibration around the fixed lattice points is possible.
Okay, sorry.
How much? When we push these two bars together, some of the energy from the hot bar is transferred to the cold bar. So, the question is, why is this thermodynamically favorable? Remember that the second law of thermodynamics states that during any spontaneous process, the total entropy change for a system and its surroundings is positive. When evaluating the entropy change, whether it is for the system or surroundings, delta S would be related to the change in the number of possible accessible microstates. Do you think that the entropy change for the surroundings, the hot bar, was positive, negative, or equal to 0? Do you think that the entropy change for the system, the cold bar, was positive, negative, or 0? Please pause the video here and discuss your reasoning with a classmate. Allow the molecules in the cold bar to access new energy levels that they could not reach before, increasing the number of possible microstates for that system. So we would suspect that the entropy change for this system is positive. But what about the surroundings? The total entropy of a system and its surroundings has to increase if the process is spontaneous. Let's use a very simplified diagram to think about the heat diffusion demo. We have two bars made of the same material. One bar is hot and one is cold. We'll look at 4 atoms making up each bar. The hot bar has more energy than the cold bar. Its atoms are moving more than the atoms in the cold bar, which seem barely to move. Now, before we put the cold bar in contact with the hot bar, let's think about each bar separately. In our simplified drawing of the cold bar, let's say that 3 of the atoms have no energy, and 1 atom has 1 quantum of energy and is at a slightly higher energy level, symbolized by the set of curved lines representing its motion. How many different microstates can this system exhibit? If we think about the different ways we can distribute the quantum of energy amongst the 4 atoms, we see that there are 4 possible microstates. If we do the same for our hot bar, where we have 5 quanta of energy that can be distributed in a variety of ways amongst the 4 atoms, we use some math to see that there are 56 possible microstates. When we brought the 2 bars in contact in our demonstration, we saw that they reached thermal equilibrium. Here, in our simplified example, we will bring the cold bar, defined as our system, and the hot bar, defined as our surroundings, together and divide the 6 quanta of energy equally between the 2. The first law of thermodynamics tells us that the total of 6 quanta will be conserved. Now, how many microstates are now possible in each bar? 20. As you might have expected, the number of possible microstates in what was originally our hot bar decreased, and the number of possible microstates in what was originally our cold bar increased. Let's see what this means for our total entropy change. We will use a relationship for entropy that was derived by Ludwig Boltzmann. It states that entropy is equal to a constant called the Boltzmann constant times the natural log of the number of microstates. When calculating the entropy change, whether it be for the system or surroundings, delta S would be equal to Boltzmann's constant times the natural log of the ratio of the final number of microstates to the initial number of microstates. The entropy change in our cold bar was positive, while the entropy change in our hot bar was negative. But remember, it's the total entropy change that matters. we see that our total entropy change for this process is positive. The spontaneous transfer of heat from our hot bar to our cold bar is consistent with the second law of thermodynamics.
Okay, that's enough. So that's the precise understanding of the second law of thermodynamics. So I wanted to get down to basically as concrete as possible description of that, because after that, everything else maybe can be less hand wavy. And there's some, there's some, a little bit of murkiness left in terms of, wow, how did they get those numbers, 56 and 20, but we can wave our hands at that point. Okay, but I hope that at least generically, let me turn this back to, oh, you should see me instead of that. Is this idea of state that's really important. So maybe you can go back to that. And that's something, a concept we can apply in many, many different situations. So I'll pause in just a second for questions, okay? But let me just say something about state and what state means. So going back to this question of like perfume molecules going through the air, or yeah, let's say that, or cream, little milk particles of molecules going through the milk to the coffee. So let's say when we take a snapshot of where the perfume molecules are, you can say at one point, one possibility is they're all over here next to the bottle. But another possibility is that they're distributed uniformly to the room, or there are a lot of different conditions where they are distributed to the room. Okay, and there are so many situations where they're all clustered over here. So there's a way to make that more precise. So we can think about how many configurations are there where the perfume is all over the place, right? And if you just even draw pictures on a piece of paper, you can just draw little boxes of air, so to speak, and just draw and plot a finite number of molecules into that distribution, you see that it's very, very, very unlikely that all of them will be still here, just scatter them at random, right, into the room. So that's the beginning of this idea of getting a sense of entropy, which is, where is everything distributed and how likely is it to be distributed in certain configurations versus other configurations. Okay. Now there's an important step here, which is implicit. I was talking about actually where the molecules actually are. There's another way to think about this, which is in terms of energy, the energy associated with the configuration. So I could draw a picture, I can talk verbally. So let's say it's verbal for now, all right? So we can say, for example, take another example, is a pile of sand, right? If you take a pile of sand, just put it there. But if you give it a little bit of shake, or even if you wait long enough, it'll tend to settle out into a flat configuration where the particles are all over the place, all over the floor, right? So we can think about, compare two situations. One is where there's a pile of sand, and say there's a certain amount of energy latent in that pile of sand. And then you can look at all the particles then laid out flat on the floor. An energy associated with that configuration. And if you do the physics, now calculate, one by one, or put them all together if you can, you get two different energies. One for the piles, higher energy, and for the flattened distribution is lower energy. So there are different ways to talk about this. What they sit on the screen, fundamental law of entropy, is that whenever you add energy to a system, we do some work on the system. It's always going to be the case that it will tend to transform such that it will tend to transform toward more uniformly distributed configurations, right? Or another way to say that is where the total energy decreases. Okay. All right. When we talk about the former definition, in terms of how many in terms of the distribution of possible states, that's what they talk about entropy. It's where it's that the measure of entropy is basically proportional to how many microstates you have. Okay, let me pause there right now. Okay, this is just so states we can think. Sorry, a comment or question so far? No. Okay.
I really, I find myself really struggling when I feel like there's like kind of two concepts of entropy that I have in my head. And one is this, they described in this video, entropy is a measure, it's the number of ways this energy can be distributed in the system. Okay, that's one. And then there's this, entropy is a measure of disorder. And I find it really difficult to put those two things together. Like the first one actually works for me. I'm like, oh, okay, there's some math here. We're doing math. I'm understanding that there's this like movement towards equilibrium, but somehow that's also considered disorder. I don't follow that. I find that in the coffee analogy, the cream goes through the coffee and it looks more ordered to me. Right? So I really struggle with this, like putting these two ideas together.
Yeah, me too. Okay, me too. So let's just take the question. I wish I had objects. So we have different possibilities. We can see that. Can you see the matrix? Okay, so we can put maybe at the beginning these perfume. Let's say there are four of them, molecules, all from near the bottle here in the upper left hand corner. And then this diffusion. Okay, what happens later on? Well, here's one possibility. Okay, just say this is one possibility, and here's another possibility. I just redraw this room. Let's just try to do the step by step. I mean, I don't know. Just try to work this out. 1, 2, 3, 1, 2, 3, 4, 1, 2, 3. Okay, and then here's another possibility. I put these spots here. Okay, right. Okay, and then I go on. I do more and more and more. All right. So, and there are, of course, a lot of combinatorial. There are a lot of different possibilities. Okay, so let's do another one. Just one more. And then maybe I'm trying to do these just, whoops, there are too many molecules here. Sorry, only 4. So that's 1, 2, here's another one. Okay. So you can imagine if you were to be very patient, that we draw all possibilities, right? Then we have my table filled with different configurations, only one of which here, or a few of these, are the ones where the molecules are clustered over here. So this thing about order is confusing. I think it is confusing, basically. But we call this ordered. We call this highly ordered, right? But really what we should be saying is that this state is very rare. There are only one of these or a few of these, but there are all these other states where the molecules are distributed everywhere else. Okay. This everywhere else is what we call disorder. Okay. Of course, it may be that this everywhere else might even look like a word. Who knows? I mean, if I'm lucky, right? Might look like, but if we say that, the letter C or something like that by magic appeared, but then you could say, well, what about all the other configurations which do not look like the letter C? That means from the point of view of looking doing character recognition, this letter C is a very particular configuration, and all these others are disordered. Yeah. It's a rareness. It's a rareness. The relative rareness of some particular that we would say that I would say something maybe we can think of as order, perhaps. That's not as here. Let me go back to. I didn't say that very well, but.
So I'm just thinking like, so when the milk and the coffee is just in some fantasy where you put it together and it didn't mix, that would be more ordered. That would be like the milk stays with the milk and the coffee stays with the coffee, and that's more ordered. Okay. Yeah. Okay.
Yeah. Okay. Yeah. You see, we're getting back to life again, right? When we talked about 3-4 weeks ago about how life is, it was called order producing systems. It has this very particular power of producing order. And I think it's worth going back to think about that characterization. What that means, because it's very complicated, right? I mean, my God, it's so complicated, but it's not, yes, it's complicated, but think about the other ways that those molecules in my body, your body, could be distributed. And most of those other ways don't amount to me. to living body. It's astronomical, I understand. It's amazing. I mean, we read Stuart Kauffman, Stu Kaufman, the biologist, and he has some back of the envelope calculations for the way that the amino acids are put together, could be put together differently than the way they are found in living tissues. And the number is unbelievably large number. It's so large that basically, I think he did some calculation on this kind where if you allow these different amino acids to recombine, quote, at random to form all possible configurations at some fantastic speed, far faster than any supercomputer, but maybe at the level even of quantum computation, it would take many, many times the lifetime of the universe to even come up with, one small organic molecule like DNA. In other words, it's highly unlikely that random configurations will give us the configuration that we see of our amino acids in living tissues. Okay, which means it's not ergodic. It's not what you call ergodic. Just mix it up. Okay. Anyway, there's some deep questions about that kind of specialness, and yet it's contingent. Contingent is not. See, that means a contingency, meaning contingency. Okay. What would you say contingency? Yeah. What would you say contingency is? Here's the question. I mean, everybody has their own. So what do you think? Versus determinist. In simple words or examples. It's not like an equation you write down. You can say plug in a 5, you get 17. Plug in a 6, you get 21, or whatever. That would be deterministic. A physical process would be like this bell, this mechanism of the bell that every hour on the hour it tolls once, or whatever. That's but if you think about history or biology, these are held up as the quintessential examples of contingent. They're not determined, but they're also not random. It's neither determined nor is it random. It's very interesting, I think. Yeah. And so that's why I use the word contingency. Other people use the word contingency, and it's actually very deep. It's not random, actually, not random. When you build in a contingency fee for doing a contract, its word is contingency, not random. Not a random fee. It's a fee that you charge 10% extra for the job, just in case something happens nobody could have predicted. Mm-hmm.
Yeah, it's like in certain cases, something will happen.
That we could not have predicted at the time the contract was signed.
Right.
Yeah. Beyond our control, Okay. So, okay, that's okay. Entropy, heat. Part of this thing would be to explore how to transfer those notions to other domains. So let me now go to the rant I was beginning to do at the beginning of the hour, which is we go to computer science. My favorite, what do we call it? Flogging target. Because you look at a computer program, let's say, say let x equal 5, and then add 1 to x, then print x, you get 6, right? Okay, so that's uncontroversial, right? But if you look at what happens in the actual computer, what's going on in there, right? Down in the hiss of the electrons in the actual circuitry, somewhere there's some piece of silicon and doped minerals, right? That you tickle with some electricity, let's say, or maybe light, if it's fancy. And the next time you tickle with electricity to inspect that register of memory, piece of memory hardware, you get back some result which you can then decode as what you put in. You read it was you put in 5, you poke it again, you get back 5. That's amazing amount of engineering actually to make that happen. Okay, asking an electrical engineer rather than a computer scientist. Computer scientist doesn't care about that part, right? So that constancy of memory is a carefully constructed illusion that's maintained. Because you look at it at the quantum level, it's hissing all the time. Right? There's all these quantum mechanical processes going on all the time. There's all this interdeterminacy at that level all the time. So it's very interesting, deep applied physics going on. And everything's bounded in such a way that we can get by most of the time. The errors are so small that in practice we can pretend that there's deterministic things going on in the computer. And also see, if you look at this question, what I just said here, if you just take the words there, what's the difference between the computer scientist point of view, computer science point of view of arithmetic, and the electrical engineer's point of view of doing operations? What's the big difference, you say? This is a question between those two paradigms. Not from the logic point of view, but from the...
I mean, the electrical engineer has to pay attention to electricity and energy consumption, right? More so than the computer scientist, or where the computer scientists also have to pay attention to energy.
Absolutely. And then what is the domain, the ontological domain that the computer scientist or logician is?
I guess it would be atoms versus bits.
Atoms, one side. Bits, let's say a bit more now. When we say bits, what can we, what other things, human-made things, are in that category of bits?
Information in general.
Information. Even any kind of like letters of the alphabet, words, CATDOG, right? Actually, we could probably throw in, mathematical symbols. We could throw in, right, the triangle, the circle.
It's, the symbolic, representations.
Yep. Okay. There's a domain called, I'm sure you know, called semiotics, which is concerned with the study of science in general. It's very powerful. So yes, starting with words like linguistics, but then going beyond that to look at any sign that is made, that can be defined. Okay. Graphic signs, and also it's been extended now to looking at, for example, time-based media and gestures too. Semiotic analysis of sign languages, right? So the question there is basically, how do people make meaning with marks? Okay, how do marks make meaning? Is another more neutral way to put it. Now, all that though is immaterial, typically. We don't have bits, right? That's what Cameron's saying. It's not the ontological domain of bits, which is a question of matter and energy. So here's why I come back to thermodynamics. In computer science, when we talk about algorithms, whether it's machine learning or computer or cleaning up a Photoshop filter, using a Photoshop filter or whatever, these are considered as logical operations that don't involve energy, right? So the question of electricity consumption never comes into play. When you write a piece of code, some fragments of code, or you apply an operator in a tool like Photoshop. Okay. Interesting. So you see this conceit. This is a conceit. This forgets that there's actual physics going on underneath all the time. It just so happens that it's pretty cheap. Well, I don't even know if that's cheap. I guess it's cheap, yeah, compared to the energy it takes to physically draw something. Probably, maybe, yeah, right, probably. But it does take energy. See, that's the thing. That was forgotten. And maybe you have somebody, you have some examples of where it's coming back to bite us. Can you point to some examples where this kind of, assumption that's cost-free?
Yeah, the whole the whole like blockchain security, that entire thing is like, you forgot to model the energy required in the system. It's actually having a real world impact.
Yeah.
Yeah.
And in fact, it does hits right there on the head. But and you want to, can you describe why that's such a huge energy drain?
I cannot.
That's a technical question. That's a technical question. But maybe some of you know about how blockchain, roughly works, right? This idea that um, that it's actually an ever more difficult computation that people need to, that these blockchain miners, these people who run those blockchain machines have to do in order to gain the right to be assigned a coin. Okay, that's underneath a token. Underneath is kind of part of the engine, part of the what is going on, different from below the level of cryptocurrency. Okay, and there's technical reasons for that. Okay, because you want to make sure there's one and only one, it's authentic, it's like a signature. These are all good properties, all right? But unfortunately, it means that it takes ever more energy to do this. The computations get harder and harder. It's like a unique signature, and then the next one up has to be different. And to be different, this model here is to be more computationally intensive than the previous. And that has to do, okay, anyway, there's a reason why that's the case. But the point is it gets more and more energy chewing up. And there's a competition because you want to be the first one. In order to get that right, you need to be the first one. So people invest in more and more money into making these massive big blockchain farms, compute servers. So yes, but that's not only that. There's also just running Amazon, right? Any kind of cloud-based service takes energy. One of my friends from MIT, Scott Miniman, was telling me about there was a position that he was being considered for at one of the largest Silicon Valley firms that was doing cloud services. This was about 10 years ago. And already then they were looking for, what was it? Global sustainability engineer, basically to basically redo all their services and all their basic systems to reduce their energy footprint, because already then they were aware that they were having global impact. So it's more than 10 years ago. So, okay. Oh, sorry. Another point. I said earlier this thing about, if you just ship from, please say your comment. You have a comment here about energy cost. Oh, yeah, energy cost. Thank you.
Yeah. Yeah, the article talks about the amount of water consumption that it takes to keep data processing centers cool. And I know it's not quite I mean, I think it is related to energy costs pretty closely. Don't really think about the very material impacts that massive levels of data collection require. And
Absolutely.
Yeah. So
Absolutely. Well, this thing about compute servers, I mean cloud services, what do you think is the biggest kind of class of software that leaving aside large language models and AI stuff, okay, what do you think is even bigger? What do you think is the biggest class of software, commercial software, that's used on the planet? Not web servers, bigger than that.
The biggest class of commercial softwares?
Yeah. Not web servers, not web browsers and the web servers.
Is it coding? Is it coding platforms? I don't know why.
Yeah, coding platforms like Xcode or whatever, IDEs, these things, they actually don't take very much energy because they only work with some strings and just process them logically. But bigger than that, much, much bigger. But think about it. To run any business, right? Amazon on down, you need to maintain records of customers and products, employees, HR. Those are on what? Databases. Yeah, exactly. Databases. Right. So that's the giant, that's a elephant of all consumers of software consumers of energy, really. So all these data farms and all this stuff, and even AI. I mean, basically AI is doing a lot of manipulations of databases of data of text or images from people, right? So it's all databases actually. And a database is basically a store of information in some structured way, right? And you have different ways you can do queries and search for them, bring them around, and manipulate different things. Okay, so but all this other stuff like coding, like an IDE or something like that, or Photoshop, or whatever else, heart monitors. It's minor compared to that. Now, why do you think we have so many databases in the world? Now we get into something. Why? What do you think is driving that? Infrastructure.
This is very much in my realm of work, and I feel like there's millions of things that, I mean, there's all of these theories about why like we're headed towards big data as like the basis of governance, basis of decision making. Like corporate advertising is such a major one. I mean, it depends on the domain, I guess, but just like this like over reliance on like information as like the guiding force for decision making. Like the more information we have, the better decisions we can make, which I don't even like, hard to say if that's true. Like it's probably really not.
Yeah, but you can't have a global economy if you don't have private property records and financial records and all the things, what I mean? It's, you first have to have like the records are kept. That's like, if you're not keeping the records, then we're just gonna like be anarchists and exchange broccoli with each other. Like,
yeah.
I think that like that. Ooh, sorry.
Go, please.
I think that's like this is like where I get kind of excited, I feel like, because this is again my realm, but like I think that's the claim. Like I think the claim is that the more records we have, the more efficient we can run our societies. But I don't, there's ways to do record keeping without like collecting minutia, and like doing this like really big datafied state system that we have. Yeah.
There are big questions here now. One which we absolutely should bookmark and come back to, like property, the notion of property, and don't forget what Leah just said. Okay, but property first. So the need to perpetuify, right? Not the need, the impetus, or the what's it called, imperative to perpetuify anything, everything, right? Perpetuify started with land, yes, but we also have the notion of perpetuifying labor by people, Marx, right? But it also has the notion of perpetuifying experience, et cetera, et cetera. Okay. But now when we go to digital economy, so to speak, we had to perpetuify I don't want to say virtual, digital algorithmic objects, services. So and then now at Berkeley, maybe it was about 1990s, they started this big wave of looking at how to make what they call information economy. So that's the question here, right? Which we can, some people here can go to and look at. I actually think this notion of IP, intellectual property, started in the 1990s as well, in a big way, when we went to digital assets and digital and algorithms, for example. Because before, perpetuification meant just something tangible, the actual chip or device and whatever, something like that. But when we go to digital forms, to perpetuify those takes a little bit of gymnastic, which I think are not completely successful. But that's a whole big topic, perpetuification logic. Behind that, you can say, well, why is there such a perpetuification? And one big answer is, capitalism, right? Under capitalism, we need property. We have a notion of property to get started, and notion of ownership in order to have owners and people who don't own them, right? So you can transfer ownership. Otherwise, where's the economy, right? In the capitalist model of economy. But as David Graeber was saying in a book, The Dawn of Everything, That's not the only model we have had in 10,000 years. So just bookmark that. Now, the other thing is the increase issue. Okay, whatever it is, suppose we do have a way to assign property, and I agree. I think not necessarily, it's a certain amount of data, but why do we need more and more and more and more, right? So now let me open the floor. This question about increase, where is that coming from?
I think, I think in addition to us needing to propertify data, there's also like an increasing need to weaponize it. So the more data you have, the stronger hold you have on people, on systems, on economies. So, but then you can only weaponize the data that you have, and so the more data you have, the better for you, whoever it is, the powers or economies or governments are. So I feel like data and information have become almost like tools used to exert sovereignty and authority over people's systems, regions. So yeah, I think, like when you go to a website and they're like, accept cookies, do not accept cookies. And then there's a whole, if you don't want to accept cookies, some just let you go, but then there's necessary cookies, there's essential cookies, there's why. It's almost weaponized, because when you accept cookies, you're giving the websites the right to take your browsing data and then probably use that to suggest stuff to you too. So the data, your browsing data, is essentially like a weapon in the hands of a website. It's in a way like a weapon maybe in the hands of Amazon to say, okay, so you bought a brown bag, maybe you need a brown hat to go with it. So it's almost, I think, in a way, the more data you have, the more you can weaponize it and exert control. And I think that also points to like capitalism and, yeah.
I think also well, okay, just said, once you've bought that thing, the profit's been made, you need to buy something else to make more profit, right? Like there is a huge profit incentive to like increase. Once you bought it, it's done, and you're not part of that anymore. So you need to buy the next thing.
Yes, absolutely. Then if we go to financial instruments, right? If we go to a second order economy, we talk about what banks produce as products, right? I think some of you are very familiar with that. This idea is that you can above the level of the individual holders of debt, like someone who gets a loan to do something, to buy a car, buy a house, then you have the banks that hold those loans, right? For them, it's property. And then they can bundle that up and sell off those financial instruments to other entities, then they can trade those things around. So now what's interesting is, again, there's another pressure, which is we would like to issue more loans to get more of those kinds of instruments to sell. Or we can build on top of those other layers of products, which can then in turn be sold. So there's another way to make money, which is actually make more combinations of entities. So that's a new product, right? So this kind of virtualization of the economy makes it easier to build bundles of higher order products. But you see, to denote all those kinds of things takes more databases, more legally airtight and technically airtight databases to record all that, right? And again, it's profit motive, right? We want to make more profit, so therefore there's an incentive to make more objects. Make more objects requires more databases to denote them. That's one branch, which is up this branch of property. Another one, I think, going with what Leaky is saying in terms of this kind of military metaphor, is this question of control. When you have a bureaucracy, this is again David Graeber, okay, who wrote this book called, what is it called? Utopia of Rules. Somebody is reading great. Okay, Utopia of Rules. Have you seen this book, Utopia of Rules? It's a great book. It's a great. You can look for it. Anyway, it's about the love affair that bureaucracy has for rules and procedures. Okay, We all live with these. So then this has this idea that if in a managerial society, such as ours, right, modern managerial society, the idea is that we have very complex systems of production and government, etc. At these different layers of administration, the manager needs to know what's going on in the subordinate layers. Okay, this would be my little cartoon, all right? In order to know what's going on, the manager needs reports. The manager needs to have data coming back to the manager, okay? And then the data, then the thing is, the manager would think, oh yeah, if I have enough of a picture of what's going on precisely, then I can say do this, do this, do that, allocate this, allocate that, right? But part of the argument that I would say, and then I'm working on with other people, is that it's an insatiable demand. There's never enough information to completely describe what's going on, especially if the processes themselves are contingent processes. You cannot predict them. And so new kinds of activities, new relationships are being formed both within the organism and also with the ambient, within the world. New things are happening. So there's never going to be enough information, actually. So there's always this insatiable demand for more and more and more and more and more information, more data. Whether it's HR or products or customer, whatever it's going to be, or military. Two big forces. But I think I'm with Leah and other people who say, look, we were doing very sophisticated, very subtle kinds of decisions before computers were invented, having to do with politics, power, marriage, whatever, kinship. Very, very, very sophisticated social and ethical, artistic constructions. And there are mathematical reasons why there are most of the kinds of creation, expression, decisions, let's say, are actually not computable. They cannot be computed or decidable. These are formal theorems. And because they're not computable, even in principle, this is a formal argument. That's another reason why I think people need more and more computers. If people try to model them with a computer, because it's always beyond reach, they're going to keep on trying and build more and more instruments to measure that which is actually infinitely far. It's a nice job, guaranteed. Okay, enough of a rant. We have a few more minutes for other questions about thermodynamics. I'd actually loop it back to thermodynamics. I for the graduate students, for you guys, there's a reference to Bataille, the accursed share by, and it's a bit repetitive, so you can just drop in, maybe at the first chapter and probably get the idea. But it's very beautiful, very amazing work. Has anybody read some of this guy, Bataille, Bataille, French guy? And he basically took a thermodynamic approach to thinking about war, religion, culture, more like a transpose of the scientific stuff more to culture, society, arts, war. It's interesting. So I might think of that as an example of where maybe you can transpose some of these ideas to your own interest. Okay. All right. Hope that's useful. And I'm interested in your responses. All right. Take care.
So do you have a minute?
Yeah, please. I'll hang out.
All right.
Hi. Yeah. Let me turn the recording off now.